In this video, we will learn about light, the rays that light produces, how they pass through different lenses, the variables involved in this, as well as how to draw a ray diagram of one of these lenses. So first, when we think of light, we think of three different types. The first is waves that you see, rays which are reflected, and photons which are particles of light. Now when we say light is refracted, we mean that it is bent. So the definition of refraction is that the fact or phenomenon of light being deflected or bent after passing from one medium to another. The two mediums could be air to water, air to glass, just two different types of materials to bend light. So the two different types of lenses that we're going to look at are converging and diverging lenses. So converging lenses work in the fact that they take rays of light, multiple rays of light, and they converge it to one focal point. And the focal point is found on the focal plane, which is also sometimes referred to as normal, away from normal. So converging on the right-hand side says that as the light rays enter into the more dense lens, because it's thicker in the middle, they refract towards the normal, towards the focal plane, and as they exit into the less dense air, they refract back away. So that's where you see them pop back up after they've passed through the focal point. Diverging lenses, however, are concave and therefore less dense in their center. So they take light from the focal point and diverge it outwards. The way they work is that as light enters the less dense material, they refract away from the normal. So remember, this is the focal plane. And they exit into the air. Converging lenses will always have, so the length from the middle of the lens to normal, as you see here, is marked as F. F is your focal length, the center of your lens to your focal point. And as you can see here, diverging has it too. So you may notice that in converging lenses, the focal point is in front of the lens. It's a little covered up, but we'll mark it again. And in diverging, the focal point is behind the lens. Therefore, in converging lenses, we always have a positive focal point, and in diverging lenses, we always have a negative focal point. So taking a deeper look into the variables involved, so we've already decided that F is the focal length. And as you can see, if you take the reciprocal of the focal length, you are given S and S prime, where S is the object's distance and S prime is the image distance. We then have a second equation that states M, which is magnification, describes how large or small the image has been made. So as you can see, we also have H prime and H, which correspond with S and S prime. So S and H describe the object, and S prime and H prime describe the image, where the H's are the heights and S's are distances. So if you look in the black box underneath that, it'll tell you the relevance of all of these variables. Specifically, magnification is very important, telling us if the image is upright or inverted, meaning upside down, enlarged or diminished, meaning bigger or smaller than the actual object, and real or virtual. So we're going to focus on drawing a ray diagram for a diverging lens. As you can see, you start off with the X and Y axis and draw the diverging lens itself in the middle of the axis at the origin. Now once you find your focal length, you will measure that from the center of the lens out to the right and out to the left. So you get a principal focal point and a secondary focal point. Then lenses account for rays coming in from the left and right, so that's why we have two focal points. Now, when we have the object's distance, so from here to here is the object's distance S. We can place the object on the x-axis, and so if we were to go from here to here for the y, we would find h for the object's height. Now how do we find S prime and H prime? We use a ray diagram. And of course, there are infinite number of rays that pass through lenses, but we focus on 3 specific rays. The first ray will be parallel to the axis. So as you see here, ray 1 is parallel to the axis and then reflects through the focal point. So that would be this dotted line that reflects back through your focal point. Now I know earlier we said diverging lens scatters light, which is this ray that we see right here. However, when we're trying to find the image, we reflect the light, or we draw these dotted lines, because the rays don't actually behave like this. We're just trying to find, well, they do, but we're just trying to find the virtual image. So then the second ray is an incoming ray that passes through the focal point and emerges parallel to the axis. So ray 2 will draw emerging, so technically if it continued, it would be emerging through the second focal point, but then it stops and goes backwards parallel. Again, this is to find the image. Usually it would scatter out straight through. The last ray we're going to focus on is a ray that strikes the center of the mirror and reflects at an angle equal on the opposite side. So it just goes straight through. Now where these 3 rays meet is the H prime, the height of the image on the y-axis, and on the x-axis is the H, is the S prime, the image's distance. So that would be H prime. Okay, so let's try to solve a problem. We have our formulas on the right-hand side. So it says a diverging mirror has a focal length of 12 centimeters. However, if you remember earlier, a focal length for a diverging mirror is negative. And it wants us to locate the image for the object distance of 20 centimeters. So the object's distance is S. So we will do 1 over object distance 20 centimeters plus we are looking for S prime image distance, and we are given 1 over 12. When we solve for S prime, we get that 1 over negative 12 is, or minus 1 over 20 is equal to 1 over S prime, which gives us an image distance of negative 7.5 centimeters. Part B asks us to find the magnification. So if we pull, we don't have the heights, but we do have S prime and S. So we can use this equation, negative S prime, which we just solved for in A, over S. Plug our values in. However, remember, your S prime value itself is negative. You have to make the whole thing negative after. So we get a total magnification of 0.375. Part C is asking us to state whether the image is real or virtual, upright or inverted. Explain how does your answer follow from the obtained signs. Match image features and signs of calculated magnitudes 1 by 1 for real/virtual and for upright/inverted. So we know that from part B, our magnification is positive and our magnification is also less than 1. So if we were to look, since we have a negative magnification, we know that our image is inverted. Our magnification is positive, so we know that our magnification is upright. And we also know that our magnification is less than 1, so therefore we know that our image is diminished. And lastly, it asks us to determine if our image is real or virtual. So the object distance S, which was given, was 20. and the focal length was -12, and 20 is greater than -12, so we know that the image is. However, when we use diverging lenses, our S prime value is negative because in this slide, as you see, it is in the negative on the x-axis. So when the image is behind the lens, we will call that a virtual image. So usually diverging lenses produce virtual images. Lastly, we are asked to draw the ray diagram that supports our answers. So first we need to start by drawing our axes. Next we need to draw our lens in the middle at the origin. And now we will mark our focal lengths, each at 12 centimeters from the center of our lens. We were also given our object distance at 20 centimeters. So for our first ray, we draw it parallel and then reflected away. However, if you remember the dotted line, it should, from the image, reflect back through the focal point. The second ray will go down in parallel. So if we were to draw its reflected image. And finally, the last ray, which will go straight through. So now where these three lines or rays meet, we know is the image. And as mentioned before, it is behind the lens. So that is why we get a negative delta S and why the image is virtual. So here we have delta S.